All right, welcome. So in this video, I want to continue talking about the minimum algorithm that we looked at briefly in the last video. But now I want to focus in on arguing that the algorithm we created is indeed correct. And we're going to introduce a couple of important proof techniques that we're going to use to establish correctness for algorithms like minimum, specifically algorithms that use looping structures in them. Will be helpful to use the technique we're going to introduce called loop invariants. So let's take a look at that. To start out, I just want to revisit what we looked at in the last video, which is here we came up with this algorithm for the minimum problem, the minimum problem of returning the minimum element in a list. Again, a very simple algorithm, hopefully one that you already have a few strategies that you might follow to carry it out, or maybe you're also familiar with this algorithm that we came up with. This is a simple sequential search through the list for the minimum element, where we're going to, again, very quickly assign the first element as our minimum so far, and this is going to be important when we get to our argument, our proof that this works. And then as we go, if we ever find an element that's less than our minimum so far, we just update the minimum so far and we return it at the end. Now, of course, hopefully all of us put this algorithm through our internal compiler, and we're able to sort of see for ourselves that, yeah, this sort of makes sense. You might think, hey, if I take this algorithm and I code it in my favorite programming language, and then I run it, it should return the right answer every time. Now, of course, there are a few places for us to get errors in that process between here, us looking at this algorithm, and us pressing run on our favorite programming language. A lot of the errors that we're used to making as programmers are what I might call implementation errors, where we have an idea like this algorithm here that we want to implement, and then we just make a mistake. We do an off by one. We do our array bounds incorrectly, something like that, and that usually results in a bug, an error that we recognize in practice as we're coding, and usually we correct it. In these cases, these are sort of copying errors, where maybe we have a perfect idea of the algorithm, but somehow when we copied that idea from our brain or from a pseudocode like we have here into that program code, we've made an error in copying. Now that's, hopefully if you're a programmer, that's a skill, a debugging skill that you're already building up to eliminate those kinds of copying errors. What I want to focus on here in this series of videos that we're going to be looking at here are errors that precede the copying errors, errors where we make errors in the design of the algorithm itself. And so even if we perfectly implemented it, it would still give us errors. And sometimes those errors, like bugs in our programs, are subtle and hard to detect. And so we need to build up an intuition and skills like we do building up our debugging skills as a way to eliminate and make sure that our starting position is from a correct algorithm. And so here I've offered you this minimum algorithm. We can maybe, again, put it through our internal intuitive compiler and say, yeah, that looks right to us. The problem with our internal intuitive compilers is sometimes they can go wrong. And so what we want to do here is, well, let's, one, build up our intuition, and then two, let's build some formal tools that we can use to maybe rely on or rest on when our intuition might let us down or is not sufficient. So I mentioned at the end of the last video that there are sort of two important questions to ask about an algorithm when we have it. Is it correct? And how efficient is it? And we're focusing on that first one right now. Is it correct? So let's continue. So maybe if we want to ask if it's correct, a helpful tool would be, well, why don't we define, spell out for us exactly what does it mean for an algorithm to be correct? Again, our own understanding of these words and our understanding of how an algorithm might work, we might already have an intuition of what it means to be correct. Well, let's put that intuition, the informal intuition, into a formal definition. So here I have a definition. It says an algorithm A is correct for a problem P. Now let's just focus on A and P here for a second. This is a bit of the formalism where we like to give names to things, just like we would name a variable in a program. Here we name some of the variables in our mathematical discussion, in a proof, or in this case a definition. So we're going to call the algorithm A, and we're going to call the problem P. And then the important thing here is that we're seeing is that this correctness relation is indeed a relationship. It's a relationship between an algorithm and a problem. So what that means is you could take any algorithm you like and any problem you like and put them together in a pair, and you could ask, is this algorithm correct for this problem? Now, if you're just picking algorithms randomly and problems randomly, the answer most of the time is going to be no, of course. You don't just pick random algorithms for your problem, but it's sort of the goal of maybe the algorithm designer or us as programmers and computer scientists is we're trying to match up algorithms with their problems. Okay. Now, I want to again stress here that this isn't sort of a one-to-one match. There isn't just going to be one algorithm for a particular problem. And in fact, this is usually a many-to-one relationship, that for any particular problem, there are many algorithms that satisfy this relationship, the correctness relationship. That means there might be many correct algorithms for that problem. And even though we're focusing on correctness right now, afterwards we're going to use some other measurements or tools to measure our algorithms beyond just correctness, to then say, if I have multiple algorithms for a problem, well, which one should I use? Maybe there are other characteristics that we could use to determine which one we should use. So, well, again, that will be the topic of a future video, so let's focus in here on correctness then. What is the nature of the relationship between A and P that makes it correct? Well, the algorithm is correct if for every input of the possible problem P, the algorithm returns the correct output for the problem P. So remember in our last video when we defined what a problem was, an information processing problem, a computer science problem, not just any old problem. When we defined what a problem was, we said it was a relationship between an input and an output. Now what we're saying is correctness of an algorithm is also a relationship between an algorithm and a problem, such that that algorithm satisfies that relationship of the problem. That is, it maps the inputs to the correct outputs. So remember, that problem statement tells us what the input will look like and what the correct output should look like for that input. The algorithm fills in that gap if it's correct. If it's correct, it will map us, it will move us from that input to the correct output. Now again, hopefully that maps right onto your own intuition of what it would seem for an algorithm to be correct for a problem. It takes in the input and then it gives you the correct output. Okay, so there we go. So again, we looked at the minimum problem. The problem at hand is the minimum, and so that means what makes our algorithm correct is if it always returns the minimum input, minimum of the input list. Okay, always is important there too, not just sometimes returns. We don't want it to just sometimes be correct. Maybe sometimes we have some algorithms that maybe if they're not correct all the time and we just can't find an algorithm that's correct all the time, or maybe not an efficient one, then sometimes we're okay with algorithms that are correct only some of the time. But if we are talking about those types of algorithms, we often will step away from the word algorithm itself, because algorithm tends to carry with it this connotation that it is correct, the algorithm is correct. So sometimes if you have an algorithm that's not always correct, we might call it a heuristic or give it a different name to stress that, oh, this isn't exactly an algorithm that we've proven correct. Okay. So again, just the stipulation of what we might expect for the minimum problem is we need to return the minimum of the list. Okay, again, fairly straightforward. All right, so how do we argue, how do we demonstrate, say, to a skeptical reader that our algorithm actually is correct? Okay, maybe, for instance, maybe you like my algorithm for minimum. I happen to like it, But other folk might come up with different algorithms. I started at 1 and counted up to n. You could have started at n and counted down to 1. And for that matter, any arbitrary order of iterating through the elements would be fine. We just need to visit every one. So that means there's more algorithms out there than just the one that we have available, and maybe you prefer yours to mine. How do you know yours is correct and mine is also correct? How do we know both of ours is correct? Maybe our friend comes up with another one that's incorrect. How do we know that that one is incorrect? Okay, how can we show that it's incorrect? Let's take a moment to just think of an incorrect algorithm for minimum. I'm going to come up with a silly one, okay? I'll call it the lazy algorithm. In the lazy algorithm, what we do is we just look at the first element and then we say that's the minimum. Now that's a lazy algorithm because we're lazy, we're not going to look at the other elements. But here's the thing about that algorithm is it's correct some of the time. If the minimum element happens to be in the first position in the list, then it's correct some of the time. That's one of those heuristics. Maybe we'll call it the lazy heuristic. Okay. However, how can we show that it's not correct all of the time is pretty easy. We just need to show some list that it doesn't work on. So imagine the list that has the elements 2 and then the element 1. Well, this lazy heuristic would return the element 2, and of course that would be incorrect. So it's quite easy to show something is incorrect, as we just did there, by giving what we call a counterexample, showing some input that it doesn't work on. Well, that also sort of highlights the challenge for proving something is correct, which is we can't just show that it's correct for some input, we need to show it's correct for all of the inputs, any old input. Okay, and so that's sort of this last bit here. So if we're trying to prove something correct, we're going to do a proof, and then that proof has to show that our algorithm is correct for any possible input. Okay. All right, so this principle that I'm talking about here, the idea that our algorithm should apply to any possible input, is what we call generality. So I have that sort of highlighted here. So for generality, that means to establish generality, to make sure that our proof works. So generality, what is that word here? General is obviously the root there. And what we're saying here is we're trying to make our proof general. If a proof is general, then it will apply to any situation, as opposed to it being specific. If a proof is specific, it will apply only to that specific situation, not in general to all of the situation. Typically, normally, most of the time, we want our proofs to be general. Why? Because if it's general, it will apply to all of the specific situations you can come up with. So general proofs just tend to be favored, preferred over specific proofs. So typically we will want to have generality. Sometimes we can't establish generality. Well, if that's the case, well, maybe we can make a specific proof. That might be good for what we've got at the moment. But if we can get away with generality, we try, which means all that often we're going to be trying to make as few assumptions as possible. When we make assumptions about our input, for instance, usually that restricts the generality in some way. Okay, so we're going to avoid that, we're not going to make any assumptions about our input. We're going to assume our input is arbitrary, okay, any old input, and that way we're going to satisfy that condition that our proof will apply to any possible input. And again, that criteria, or that establishes the property of generality for our proof and for the theorem that we eventually prove. So let's take some of these principles that we've just introduced here and apply them to the problem at hand, which is minimum. Now here, for our convenience, I've listed the problem statement. This is the problem, this is the P, and this is our algorithm, this is the A. Okay, so if we want to prove our algorithm is correct, we're trying to establish a relationship between these two. This algorithm is correct for this problem. And as you'll see here, I've used the same name for the algorithm and the problem. This is sometimes something that we do that can be confusing, actually. It's a little bit confusing. If I wanted to change this up to make that a little clearer, I might call this sequential minimum. because we are sequentially searching for the minimum as opposed to maybe some other strategy. Okay, to highlight the strategy, highlight the algorithm as opposed to the problem. Here I've kind of named the algorithm after the problem, which again, conventionally we do a lot, but can be confusing. Okay, so looking at the minimum problem, it's establishing for us what does the input look like. A is going to look like this, and I talked about this a little bit in the last video, but let me highlight again some assumptions here. Just because notationally I've written it in this way does not assume, some of us might look at this and assume there must be at least 1, 2, the dot 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 sort of implies there might be something more in there, maybe 3, and then n is maybe 4. Some of us might look at this and say n has to be at least 4. Well, that's not really how this notation works. Here, if I haven't said anything about n, we should assume any reasonable n could be plugged in here. For instance, n could be 1, which would mean that there is no a2, and in this case, an is equal to a1. They're the same value, okay? This notation is just to indicate that we start counting at 1, we go up by 1s, 1, 2, and usually that's the normal notation, and we're going to end at some natural number n. If there's some condition on n that we want to place, sometimes we'll add that as part of the condition here, and n must be greater than or equal to 4, for instance. Now, when I mentioned this last video, and I'm going to highlight it again, I said 0 is usually a reasonable choice for n as well. It's at least one of these border cases that we should be considering on our input. But I also mentioned that the minimum problem ceases to make sense because we are supposed to output one of the elements of A. If A has no elements, the output is undefined. It doesn't make sense anymore. So I've said for our purposes, let's assume at least n is going to be at least 1. That way making sure that the problem is well defined. But otherwise, we're just going to assume our A comes in. It's of this form. We don't know what n is. It's any natural number greater than or equal to 1. And by assuming our input is of this form, that's the arbitrary input business that we were dealing with down here with generality. So assuming our input is of this form, that we know nothing else about it, we don't know what the actual numbers are, A1, A2, and so on. We don't even know how many there are, only that it is 1 or 2 or 3 or some natural number. Okay. Then what else does the minimum problem do for us? It establishes the output, what we should expect for the output. Let's go through the notation here again. AI is an element of A. This is telling us that what we're supposed to be returning is one of the elements in our sequence. Okay, such that, which element? Such that AI is less than or equal to AJ for all of the other AJs that are in AI. Remember last time I mentioned that this establishes that AI must be less than or equal to itself. Well, it's equal to itself, so that's okay. And it will be less than or equal to all the other ones if it happens to be the minimum. Remember we talked about some weird cases, maybe they're all the same value. Well, then each one would satisfy this definition because each one would be less than or equal to all of the others. They'd all be equal to each other. Okay. So this is this minimum problem is establishing for us what we need to prove correct. So I've taken that, the minimum problem, and I've restated it here just as a statement of a proposition that we want, that might be the theorem that we want to prove correct. Okay, so here we have, to prove our algorithm correct, we must show that. After the rest of this is the proposition, the theorem that we're trying to prove. Okay. The word that in English often is used, at least when we're using it in logic like this, to signify that what you're about to hear is a proposition. So the most common way that we might use that in that way would be when we want to negate a sentence. We will often say something like, it is not the case that, and then we would state the other proposition. So here, that word is just showing up again using this sort of logic ease, as I mentioned before, the language of speaking in logic language to just make it clear what we're trying to emphasize or what we're trying to say. So here we're saying, what must we show? What is the proposition that we want to show if we want to show our algorithm is correct? It's this one that comes after. So what is it saying here? It's saying for any input A of this form, remember that's the generality bit here, we return some M that's equal. So this business here, I'm merging what's going on in my algorithm with what's going on in my problem statement here. What do we return? We return M. So here I'm saying if we want to argue our algorithm is correct, the M that we return has to satisfy this output condition. So here I'm saying M has to be some AI that's in A, and the rest of this is just really copying down the output condition such that M is less than or equal to AJ, for all the other AJs in our list, in our sequence. Okay, so again, all we've done here with this minimum problem and minimum algorithm is try and highlight for ourselves what is it that we need to prove correct, or sorry, what proposition is it that we need to prove if we want to prove our algorithm correct. And it's this one here we've decided, which really is just a way of taking the input and the output here and sort of translating it into a proposition. Okay, so I've done that here. I've brought the algorithm along, but I left the proposition on the other slide to make a little more room. But I've now translated that statement into a theorem. So if minimum is called on this input, this is the arbitrary generality bit, then the minimum algorithm returns a value that satisfies the output conditions of the problem. Okay, so we've got input and output built into our theorem here. Okay, so I just want to highlight some of the challenges that this particular proof is going to pose for us. We've done a couple proofs in our previous videos, but we're going to introduce a new technique here because what we're trying to prove here is something that applies to any n. And sometimes we've actually done that in the past already. We've proved that, you know, any odd number, if we multiply it by any other odd number, gives us an odd number. Same thing with evens. And we were able to do those proofs very quickly and easily. We established the generality of them, or we were able to maintain the generality of those proofs very easily without having to introduce sort of some secret new techniques, unlike what we're going to have to do here. And so we're faced with the problem here of having to prove infinite cases as well. But now each of the cases can't all be handled all at once necessarily, like we did in those previous examples I mentioned with even and odd numbers. Now all of these infinite cases, we're going to have to, you know, one strategy might be handling them one at a time. That's unfortunately problematic because we don't have infinite time. So we have to use sort of a clever technique, and that technique that we're going to use is called induction, or more specifically mathematical induction, that allows us to basically get infinite proofs all with one single proof. You might think it's more than one single proof. It's got different parts, so maybe it's 2 or 3 proofs in one. But with that small finite number of proofs, you're able to establish an infinite number of propositions, or a proposition that applies to all elements of a particular class. And that's what we're trying to do here. Now, our inductive proof is going to have 2 or 3 main pieces depending on how you adjudicate things. I usually call it 3. We have 2 places where we're actually proving things, the base case and the inductive case, and then we have a hypothesis that we make along the way we call the inductive hypothesis. Let me show you how this works. Okay, so to do this proof, this inductive proof, we're going to also, so the proof that we're going to provide here, I guess I should say, is going to be an example of 2 different kinds of proof. One is an inductive proof, like I just mentioned, and the other is the proof of a loop invariant. So let's take a moment before, again, we dive into the proof to look at what this principle is, this idea, this concept of a loop invariant. So first of all, the term invariant is a term that shows up in computer science in more than one location. The word invariant means to not vary or unchanging, something that does not change. And it shows up in computer science a lot, or the way that word shows up. Why do we use that word instead of not changing, or immutable is another word that means not changing that we use in different places in computer science. So why do we use invariant, or what is the purpose of it in our theory? The purpose of invariant is to show that something doesn't change after we do something to it. What might we do to it? Well, invariants show up a lot in data structures, which is something else you might be studying if you're studying computer science, where for a data structure, we want to establish an invariant, a principle or a property of the data structure that will not change after what? After we do something to the data structure. What do we do to data structures? Usually we add data or we delete data. So we want, and here's a good example, if we have our data stored in a tree, after we add data, we want it to still be a tree. And after we delete data, we want it to still be a tree. If it's not, then we've somehow violated an invariant for that data structure. Well, we're introducing the principle of invariant here with respect to a loop. And so we're calling it a loop invariant instead of, say, a data structure invariant. The loop invariant is trying to highlight or identify a principle, a property, that remains true after what? After an iteration of the loop. So with data structures, the thing we do that we want our data structure to remain the same after is some kind of operation. We add or subtract data. In the loop, the operation that we do where we then again want this principle, this invariant not to change, is we iterate the loop. We go through one iteration of the loop and we want to see what is still true at the end of the loop. Okay. Now, any property, so here we've got the definition, so let's look at the definition. A loop invariant is any property that remains unchanged after an iteration of the loop. That's any property, okay? So there are lots of properties that remain true after an iteration of the loop. Let me start with trivial ones. So 1 + 1 = 2 after every iteration of this loop. That is technically a loop invariant for this loop. It is just a boring one. What makes it boring is it's not helpful in any way for us to prove something interesting about this loop. And what are we trying to prove about this loop? That it's correct in some way, right? That's ultimately what we were trying to prove. So does the knowledge that this loop doesn't violate simple rules of arithmetic help us? Probably not. Okay. So what other properties might be true after a iteration of the loop? Okay, well, one thing we might be able to say after the iteration of the loop is n is always greater than or equal to 1. Well, we don't change n here, so this is another one of those sort of maybe trivial properties. Okay, we don't change n. We could prove that. If we wanted to prove that n doesn't change throughout this loop, we could use a loop invariant to prove that. I don't know why that would be important, but maybe we use n down the road later on in our algorithm, and we want to say, hey, this step doesn't mess it up. We could maybe prove that. That's a trivial one, but it's maybe not unimportant, like the 1 + 1 = 2. It might show up down the road as being important. We don't mess up a here, or we don't mess up n here. For that matter, we don't mess up a here either. We don't change any of the values in our list a, right? We could prove that too. That's another invariant. But the purpose of trying to come up with an invariant here, we're not just doing it willy-nilly to come up with all the properties that might remain true. We want to highlight and focus in on a specific property. Which property? The one that's going to help us with our current purpose at hand, which is to prove correctness of our algorithm. Are there any properties of this, any properties, any propositions that we can come up with that will be true of maybe the variables in this algorithm after each iteration that will help us prove this algorithm is correct? Okay, now there's two sort of ways we can do this. There's two ends and we're trying to meet in the middle, so we could start at either side. Where are we trying to get? At the end, what is it what we're trying to prove? We're trying to prove this is correct, so that means we're trying to prove at the end some property about m. We want to say at the end of all of this loop, at the end of every iteration of the loop, that m is what? M is an element of a, so it's not some random number we picked. It has to be one of these a1 to an, and it's supposed to be less than or equal to all of them. That's what we're trying to prove. Now remember, here's where I'm trying to pump your intuition a little bit, is when we designed this algorithm, we kind of gave a name to ourselves in our brain of what m was supposed to be. M is actually a terrible variable name, right? Hopefully, if you've taken some coding classes, your coding professors have told you, no, m, you should give it a better name. Now, why did I pick m? I picked m because it meant to stand for minimum, right? But even minimum's a little bit misleading, because when we designed the algorithm, what we actually were saying is m is the minimum so far. And here's where I would really want to focus in on that principle and that property, because that's the property that's going to help us argue at the end of the loop that m is the minimum so far. Well, if it's the minimum so far, and so far we've got through everything, then that's the critical argument we want to make. If m is the minimum so far, then at the end it must be the minimum of everything. Okay, so here I'm working my way backwards. What did I want to prove? I wanted to prove that m was the minimum of everything, and this idea that m is the minimum so far is going to help me get there. So that's the loop invariant that we want to prove correct, is that m, after each iteration of the loop, m is the minimum so far. It's not the minimum of everything, but after each iteration of the loop, we sort of add one more element that we now know m is the minimum of all of those elements. Okay, so let's see if we can express that a little bit differently. So here I've got that, sort of formalize it. So here I kept saying minimum so far. We can throw that up in quotes if we want, scare quotes, because we need, that's informal language. When the so far is sort of sloppy natural language that sort of says to our listener, you fill in the details there. I don't want to, I don't want to tell you the details, you figure it out. So, but we are those people that need to figure it out. We're formalizing it now. We need to turn this into formal mathematical notation. So that's the next step. So what does it mean, the minimum so far? So here, the so far part, I need to first formalize, what does it mean? What do I mean so far? I mean after some iteration. Which iteration? I need to give it a name. So I'm going to call it iteration I. Okay, after iteration I. Now, why did I pick I? And let's just say, well, I already used I as my iterator here in my loop. So I is actually a very nice and convenient variable to use, to reuse here. And when you have the opportunity to reuse a variable from the actual pseudocode for your algorithm in your proof, we usually do that, okay? If it's carrying the same meaning. If it's not carrying the same meaning, then we might set up some other variable, okay? But in this case, we're going to use I. So after iteration I of the loop, what am I trying to prove? Well, you'll notice this statement here, m is an element of A, m is less than or equal to aj for all aj. If we blurred our eyes and we didn't look too closely at this last term here, this looks almost like the output condition. The only thing I've changed is again, trying to cash out the so far bit, the minimum so far bit, is so far means not all the way up to an, but only up to whatever iteration we're currently on. Now let's go back and make sure we've got this right, okay? Let's look at the principle again. It says after iteration I, okay, so let's look here. My first iteration is actually iteration I equals 2, okay? When we're done the iteration I equals 2, we will have compared m, which was A1, to A2. And very simply here, I'm going to wave my hand and jump over a few steps. M will be the minimum of those two, right? If it was A1, then we don't make the change here. If it was A2, we make the change here. So after iteration 2, I equals 2 here, M is the minimum of A1 and A2. So let's, again, go back to our bit here. Is that what we're saying here? After iteration 2, I equals 2, M will be the minimum of all the elements from A1 up to where I equals 2, A1 and A2. So that's right. So why did I go back and go through that? I was looking for an off by 1 error. Okay, maybe I meant I plus 1 here and then up to I. Or maybe I meant only up to I minus 1 here, or something like this. I was just checking that indeed after iteration I equals 2, our loop, I did a quick head check. That looks like the proposition that we need to prove. Okay, so again, how is this going to help us? Well, when we get to the last iteration will be iteration I equals n, and then I here will be n, and that's what we're trying to prove for our actual proof of correctness. Okay, so now let's talk about how we're going to do the proof. We're going to try and prove this theorem, but I still need to carry out this proof. How am I going to do that? Induction, as I mentioned, is the tool that we're going to use. And to do that, we're going to split into two kind of parts, sometimes three, or we sometimes describe it as three parts. But there are two sub-proofs, if you like, the base case and the inductive case. The base case is usually kind of the simpler one. For our example, we're going to just prove for I equals 1 that our theorem is true. That's easy because it's a specific case, not a general case. Okay, and then we're going to prove a very interesting proposition. That's saying this is how induction works. It's saying if the proposition was true for the last value of I, then it must be true for this value of I as well. Notice how this relational truth sets up. Then if it's true for 1, then it will be true for 2. And then if it's true for 2, it'll be true for 3. And if it's true for 3, it'll be true for 4. And this allows us to get infinite possible cases here. Now, we're not doing it for infinite. As I mentioned, we're going to do I equals 1 to set it off. That's our base case. Then we prove the inductive case that says if it's true for I, it must be true for I plus 1. So that allows us to establish I equals 2, which gives us I equals 3, which gives us I equals 4, and so on. But we stop at I equals n. Some inductive proofs, we're trying to prove things for infinity cases, in which case we will never stop. It will always go. But in this case, we'll stop at n because that's when we need to. Okay, so this two-stage type proof, where we prove a base case, which is just one case, some specific value, is called the base case. And then the second case, the inductive case, where we do this, if it holds for I, it holds for I plus 1, call that the inductive case. Putting those two together gives us what we call mathematical induction. Okay, so I think we're ready. We've got all the pieces together. The mathematical induction is sort of it's got a lot of what I call mathematical machinery involved. It's got a lot of pieces that you need to put together to make it work. We finally gathered all those pieces before us. Let's put it together. Let's assemble the proof. Oh, I missed something here before we do our proof. This theorem is not exactly what we were trying to prove. We were trying to prove that the minimum algorithm is correct. Well, I've got stated here that that's going to be a corollary. Now remember what a corollary is it's a theorem that just follows automatically for free. Okay, after we're done proving the theorem, the proof of correctness for the actual algorithm will be very simple. I will fill it in, but it will be very simple. Okay, so as I said, let's try and tackle the proof of the loop invariant here by using our new technique, induction. And I'll go slowly through it so we can highlight the different parts. Okay. Now, the other thing I want to say about, I think I mentioned this in one of my earlier videos, but I'll highlight it a couple times, is that a proof is a mathematical structure, but the purpose of a proof is to be read by some other mathematician to understand the proof and the theorem that you're trying to prove. And so in that way, I also think a proof is very similar to a program. It serves multiple purposes. One is the actual proving. The program itself has to work, right? The proof has to actually work. But then parts of the proof are intended for the reader to try and better help the reader understand the proof and follow the proof as we go. And so that's how I want to start out here. My proof here is, as I've put here in brackets, I put by induction on I. Now why is that? Well, that is not important. It's not necessary for my proof. But it is important for my reader to know that what I'm going to do is try and write an induction proof. That helps them understand when the next thing they're about to see is my base case, they'll be like, Oh, that's what I expected to see because you just told me you're about to do an induction proof. Okay, you don't need to put that there, but I usually put it in there now, and that's because I follow a principle when writing my proofs, which is when you write your proof, you tell them what you're going to do, you do it, and then you tell them that you're done, that you've done it. Okay, and so this is step one. Tell them what I'm going to do. Proof by induction. Induction usually requires a variable that we're going to iterate over, right? We start with our base, and then we use the induction to sort of iterate as we go up. And so we usually need to name what variable we are using induction on. In this case, it's going to be on I. Okay, so what is my base case? I've decided for base case to be I equals 1. Now, if you've got the code in front of you, I don't want to flip back to it, but in the code, we started our for loop at I equals 2. And again, this is a common way to run a minimum algorithm. Okay, that means if we're saying iteration I equals 1 here, we're actually talking about before the loop. And usually when we're proving a loop invariant, the base case that we want to establish is, well, what do we know before we enter the loop? And then we'll use the loop invariant induction to handle what happens in the loop. Okay, but before we get in the loop, what do we know? Now notice here, because we started our loop at I equals 2, before the loop for us is I equals 1. Now more commonly, our loops start at 1, which means before the loop might be I equals 0. And then some of you might say, hey, a lot of my loops start at 0. Now, that's probably true if you're writing code and it's in specific languages like C or C-like languages like Java, JavaScript, and so on. Those languages have indexing starting at 0. Other languages, indexing starts at 1. And usually in pseudocode, indexing starts at 1 too. Why? Just because our math normally starts at 1. It works better when you start counting at 1. Only the computers really care about counting at 0. So most of the time we're going to be in our pseudocode, in our algorithms like we have here, we'll be starting at 1. In our case, we started at 2 here. But maybe the math lines up better for some algorithms when we start counting at 0. Or maybe you just like counting at 0. You've got that programmer hat on most days, so you just like start counting at 0. If you started your loop at 0, then before the loop would be I equals minus 1. That's sort of strange for us to set up sometimes and think about. But if we want our base case to be whatever's happening before the loop, we usually just go to the loop and we take a look there and we say, okay, well, what is the first iteration? I equals 1, then before the loop must be 0. I equals 0, then before the loop must be I equals minus 1. And we'll just pick whatever value of I comes before the loop. So again here, my base case, I'm trying to let my reader know again which case I'm doing, I equals 1. Okay, so what are we trying to prove then in the base case? Is we're trying to prove the theorem is true, but only for that restricted or specific value of I that we're interested in. So let's plug in 1 into the statement up here and see what it says. So it says after iteration 1, remember iteration 1 doesn't exist, that's before the loop, so we can translate that out if we want. We could say before the loop begins, m is an element of A, and m is less than or equal to aj for all aj. Now remember, we selected here I equals 1, so this will only be the set a1, which is what I've got written right here. Okay. So what we need to prove is that m is in A and it is less than or equal to just a1. That's the only one that matters. Now remember, prior to the loop, the very first thing we do, well really the only thing we do in the algorithm before the loop, is we initialize m to be equal to a1, the first element of our loop. So a1 is an element of A, so we satisfy our first condition here. Is it also true that a1 is less than or equal to all the aj's in the set a1? Yes, it is, because a1 is equal to a1, so that means it must be less than or equal to itself. And so we've satisfied this condition here. Now, we actually had to go through here and verify it, and we did. Okay, and we found out that it is correct. So often what we're going to do here is put a little check, or I usually put a little check mark next to my proof here saying, I'm done this part of the proof. What I was trying to prove was just that the theorem holds for just this value of I, and I've shown it holds for this value of I. Now, if we wanted, we could now pick the next value of I equals 2, and show that it works for that one too, and I equals 3 and 4 and 5 if we want to. But that's tedious work that is actually going to be wasted effort, because we ultimately don't know how big n is, and we don't know how many times we're going to have to repeat that. And we want it to work for any n. So what we're going to do next is we're going to set up an inductive hypothesis, which is going to allow us to do the inductive step. Okay, now here I've just highlighted 2 more pieces of the proof. The first bit is the base case, or the base step. Now we're going to do the inductive step, or the inductive case, and there's usually 2 pieces to that. One is we need to set up the hypothesis, and then we'll prove something based on the hypothesis. What do I mean by that? Well, remember, the way that it works in induction is what we're going to do is we're going to assume that it already was true for the previous case. In this case, let's say case I. And then we will prove that it is true for the next case. In this case, let's say I plus 1. So the hypothesis that we're setting up is the assumption that it already works for the previous case. So that's going to be the next step here. And we call this our inductive hypothesis, assuming that it works for the prior case. So here what I'm saying is assume that prior to iteration I plus 1, that the theorem holds. Now, this prior to iteration I plus 1 is logically equivalent to after iteration I. Okay, after iteration I. After iteration I is equivalent to prior to iteration I plus 1. So the statement here is exactly the same statement that we have written up here. Okay, m is an element of A, m is less than or equal to aj for all aj up to and including ai. Okay, so again, we're going to call that, this is our inductive hypothesis. We're assuming that prior to iteration I plus 1, or after iteration I, if you like, that this is true. What we're going to try and argue in this step then is that after iteration I plus 1, so here's what we said is happening before this iteration. We're going to now argue what happens after this iteration. Okay, so again, I want to sort of focus in, well, what do we need to prove? We need to prove after this iteration, after iteration I plus 1, that m is still an element of A. We haven't messed up. We haven't swapped it out for something else. And that it is now still this principle here, except that instead of up to and including ai, after iteration I plus 1, it should be up to and including ai plus 1. Okay, so we want to include that one extra element. Now, luckily, what do we do in iteration I plus 1? We compare m to exactly that element, ai plus 1. So now we're going to use what we do in the code, what we do in that step, to make this argument follow through. Okay, so now, I guess I should mention, we're now in cases I is greater than or equal to 1. Now up here we said what happened after iteration I. Now we're going to be saying what's happening after iteration I plus 1. The first case we'll do is when I equals 1, so that would be I plus 1, if I equals 1, will be equal to 2. And that was sort of the proof that we just did in our head intuitively earlier when we were looking at our theorem. Okay, but here we're going to need to make this general. This will apply for I greater than or equal to 1, not just 1. So we can't assume I is equal to 1 here. We're only assuming I is greater than or equal to 1 here. Okay, now I'm going to start us out here by, again, doing a little bit of that, telling my reader what I need to show. And we just said this as we were setting this up. What do we need to show after iteration I plus 1? That m is still an element of A, and it is now less than all the elements up to and including ai plus 1. Now, what do we know by our hypothesis? We assumed that m is already an element of A, and is less than or equal to the first I element. So what we already know about m going into this iteration is we already know it's the minimum of the first I elements. That's what the inductive hypothesis allows us to establish. Coming into this iteration, we already know m is the minimum of the first I. Okay, so now what we need to show is that after this iteration, m is still an element of A. We don't mess that one up. And the only difference between these two principles here is that extra element, AI plus 1. If m was already less than all the ones before, afterwards, hopefully it still will be. Okay, so now we just need to figure out that last case. What about m? Can we argue that m is less than or equal to AI plus 1? Now, here's where we need to again think about that the pseudocode. What do we actually do inside the iteration? At this step, we do a check. We check to see if m is, well, we compare m to AI plus 1. If AI plus 1 is less than m, so the opposite of this case, we do the swap. Otherwise, we don't change m at all. So that's two cases we actually need to consider. And so our proof continues now by splitting it into those two cases. And the way I usually present cases is the easy one first. How do you know which one is the easy one first? You don't usually. You try them and you go, oh, that was the easy one. So when you write the proof, like I'm doing here formally, I'll put it first. When you're trying to solve the proof, it might come second or third or wherever it showed up afterwards. So the reason I'm making this comment is for you, the reader, again. If you're reading this proof, when I made this proof, when I wrote this proof, it didn't just flow out of me flawlessly. That's just like writing a program. When you sit down to write the program, it doesn't just come out perfectly the first time. You go back and you change and you change and you change. So this proof that you're witnessing right now is the final version of the proof. I recognized which was the easy case and I put it first. So which is the easy case? Is the case where we don't do the swap. So let's see why that is. So case 1 is the case where m, the minimum so far, is also less than or equal to the next element that we're checking. That means the minimum so far doesn't need to be changed because it's still the minimum after this step as well. So as I point out here, in this case, we don't change m. Okay. Then I just put this here. So this case is trivially true. That is a big warning sign. That's a red flag to me. Okay. If ever anyone tells you something is trivial, then that probably means that maybe they don't really know that it's true and they're trying not to argue it true. Now this one is pretty trivial, but you should still maybe challenge someone. Trivial? Why is it trivial? What makes it true? Well, let's see. What is it that we need to prove here? Well, I just argued up here that m, what do we know about m already? We already know it's an element of A. So if we don't change it, it's still an element of A, right? Pretty trivial. That step, trivial, right? Okay, next step. What did we know about m before? We knew it was less than or equal to all of these AIs, all these AJs, sorry. After this step, we haven't changed m, so it's still less than all these AIs. Again, trivial, right? No, we don't need to really make that argument. We haven't made a change, so nothing changes. The only extra condition that we needed to argue, remember, that's what we said here. So we must also show that after this iteration, m is also less than or equal to AI plus 1. But in this case, we effectively said in this case, to start out, we said, assume that's true. Well, if we assume it's true, then trivially it's true. So we're done. So basically we're saying in case 1, if the minimum so far is also less than the next element, then we don't make a change, and we didn't have to make a change because it was already the minimum up to and including this point. Okay, so what about the other case? So if that first case is trivially true and we really didn't need to prove anything in that case, what about the other case? Well, of course this case might be the harder one because this is the case where we actually make the swap. We actually swap out our m for the new value of m, which is going to be a plus 1. So that's how I start out this case as well. I say, well, in this case, we set m to be equal to a plus 1. Again, here I put m is greater than that. Well, technically in the test we'd say if ai plus 1 is less than the minimum so far, then we replace it, right? So in this case, again, what are we trying to prove? These are the two principles we need to prove. The first one is when we set m to be equal to a plus 1, it is also clear, trivial, that's another one of those warning signs, that m is an element of a. Okay, well, sure, a plus 1 is also an element of a, so we're good. Okay, also it should be pretty clear that m is less than or equal to a plus 1 after this change because it's equal to a plus 1. Okay, now the last thing we need to do is we need to confirm here, did we mess anything up for our other principle? Up here we said m was already less than or equal to all of the a1 up to ai. By changing m to the new one, ai plus 1, we at least in principle have the possibility of messing up this as well. Luckily, if we are familiar with how less than equals to or less than works, since ai plus 1 is less than m, and before m was less than or equal to all these other ones, a is smaller than that, so ai plus 1 must be smaller than all of these values as well. Okay, so the idea here is after assigning m to be equal to ai plus 1, this principle is still true. Meaning, here we have m is less than or equal to the last element. Here, this is we're just stating that m must also be less than or equal to the first I elements. So we're after case 2, we are indeed satisfying the conditions. M is still an element of A, and it will be less than or equal to all of the elements up to and including now ai plus 1. Okay, so let's again focus on what we've done here in the inductive step. We assumed that something was true in step I, and we used that fact to argue that same principle would be true after step I plus 1. And that same principle again is what we've been calling a loop invariant. Okay, so we've now made that argument. Now what that means again is it starts that sort of positive feedback loop that if it worked for I, then it works for I plus 1, then it must work for I plus 2 and I plus 3 and so on, all the way up to any value of I that we want to get to. Okay. Now, we're not exactly done the proof yet. We usually finish off. Like I said, my proof strategy is say what you're going to do. Oops, this one here, by induction on I. Do it. That's what we did here in the middle. And then say you did it. So usually we're finishing off this I sometimes call the post-amble. This is the preamble, which comes at the end that says, okay, by induction on I, we've shown, and then usually what we're doing is restating just the theorem here. We've shown that after iteration I of the for loop, this principle holds. M is an element of A and it's smaller than all of the elements. Okay, so that established this inductive proof. This is our first inductive proof. I'm going to have a couple videos coming out after this that will, establish loop invariants for other algorithms we're going to look at. But this is our first example. It's got a lot of machinery, as I mentioned in there. It's a little bit hard to sort of digest the first time through. But if you're leaving this video with sort of an understanding saying, hey, I think I followed that proof kind of made sense to me, I get how it kind of works, then with a couple extra examples under your belt, hopefully in the next couple videos coming up, you'll start to get an intuition of your own and your own ability to sort of tackle these inductive proofs. Now, that's not the actual end of this video. I want to finish with the actual proof of correctness, which I sort of started the video claiming I wanted to do, prove that the algorithm that we've got is actually correct. Well, we kind of did it. We did all the heavy lifting there with that inductive proof. Now this is sort of just putting the finishing polish on, if you will, the last little bit to make it look nice. We wanted to argue that the minimum algorithm was correct for the minimum problem. Here I've restated the problem again. Remember, that's trying to show that for an arbitrary input, we get this output. Okay, follow through my simple proof. This is a fairly simple proof, but some of the steps, maybe again, as we're learning about proofs, maybe we're not 100% familiar. So let's see, how do we start this out? Well, if we want to start this out, we need that arbitrary input. We can't say assume A is 1, 2, 3, 4, 5. We need to say assume A is this form, arbitrary. So assume our input is an arbitrary sequence of integers. Any old one will do. Okay, then what? Now, for this to be a corollary, we need to rely on that theorem we just proved, the proof of the loop invariant. So we need to rely on that. So here I'm going to go and pull out that loop invariant theorem. The whole purpose of proving a theorem like that is to now use it somewhere else. Okay. So according to the loop invariant, what do we know? We know that after iteration I of our loop in the minimum algorithm, m is an element of A and it's less than the first I elements. Now here's where we're going to say, in particular, after iteration n. So this is saying something general, any old iteration. This is saying something specific about one particular iteration. Which iteration? The last one. Usually that's the one that we care about. What happens after the last iteration? After iteration n, so all I'm doing now is substituting in for I here with n. So now m is an element of A, and m is less than aj for all the aj's up to and including an. Well, this statement here looks amazingly like the problem or the output that we have up here. The only difference here is that here we called it this ai instead of m. Okay. So because that's just a naming difference, we can see that that property or that principle still holds. So we can indeed say that that is the correct output. So after iteration n of the loop, we return m. So we return the element that is the correct output for our problem. I was almost said for the algorithm. The algorithm returns the proper output for our problem. Okay. All right. So that was sort of a very deep dive into the idea of a loop invariant and the concept of how we can use that loop invariant to prove an algorithm is correct, to complete a proof of correctness. And so this is our first example of a loop invariant proof, our first example of an inductive proof, and our first example of a proof of correctness. So we got a whole lot of things out of the way here in this video. But like I mentioned, in the next couple videos, we'll redo that a couple more times with a few other examples. We'll continue to use algorithms as our examples, and we'll continue to use algorithms that hopefully are fairly simple to understand, so we can focus instead on the proof machinery, induction, and loop invariants, some of the stuff that I want to be the focus of these videos. All right, thanks a lot for watching this video, and we'll see you again in the next video.